Может, еще там на входе чип засканировать. Всего-то нужно, чтобы в телефоне NFC было.
А, у меня NFC.
Телефон без NFC.
Я, кстати, когда купил, думал, с NFC, потом смотрел, NFC нет, а я дедушка с карточкой.
Дедушка замшелый. Кругом. Кругом обман. Кругом жульничество. Ладно, 3 минуты еще есть. Дедушка Вилсон Лонг смотрит. Вилсон Лонг смотрит и... Что же вы не понимаете простых вещей?
Да.
Мы не понимаем. Базовая теория симметричных компонентов. Почему, как?
Они опаздывают. Там 13 автобус, это общежитие, который в самом конце города. Он, короче, приезжает где-то 20 минут. И, короче, на нем делают все.
Это убийство. Дело не в автобусе.
Нет, раньше.
Дело в неумении планировать время. Неумение управлять временем.
Нет, и как может быть? Может, это просто типа безразличие. Потому что в моем случае я высадился на предыдущий автобус, чтобы приезжать там, за 40 минут, чтобы не опаздывать.
Это очень глубокая вещь. Почему одни люди живут во времени, а другие люди им управляют?
И все равно не понимаю философию. Управлять временем.
Да, управлять временем.
Ну, минуту же назад не перенесешь.
Минуту назад не принесешь. Но добиться того, чтобы нужные события произошли планировать вперед. Когда египетскому фараону докладывали, разлив Нила предполагается тогда-то и тогда-то, а засуха возможно тогда-то и тогда-то, поэтому что делал фараон? Создавал запасы зерна, предполагал эвакуацию населения из зоны затопления и так дальше. Событие еще не произошло, а действие уже сделано, уже делается. Управление рисками. Будь там, где ты нужен, там, в тот момент, когда ты там нужен.
А он же лекцию на ютубе записать.
Черт.
Сколько вообще трудов? Я один? Не стали один.
Угу. Так и есть.
Осталось много минут.
Ой, трата времени. Ладно, надо арбайтом. Так. QSGB. What I'm looking for today. Filters with feedback. Not simple filter with feedback. You can create very effective filter if you use frequency dependent circuit in with positive feedback. Filter with positive feedback. Look at this schematics. L1, L2. Here will go C1. Operational amplifier plus L3 of minus 1 divided by L3 minus again ground, and I need this is output. This will be C2. Output feedback. This is one of the popular example of filter known as a silent key design. Silent key design is very effective. It really yields a good result, but silent key, because it has positive feedback, requires what it requires? It requires precision in design, or it will be unstable. For silent key, it's important function is alpha, amplification ratio, 1 plus our omega g, C1 R1 plus R2 plus 1 minus alpha R1 C2 our normalized frequency plus omega g square R1 R2 C1 C2 normalized frequency square. Here is the general transfer function normalized of sound and key function. In the design, this R3 and 1 minus alpha R3 is a negative feedback circuit, and it sets alpha 0 point, starting point amplification rating. Positive feedback goes through second capacitor, through C2. To perform calculus of sound and key. Sound and key it's really good choice, but calculating sound and key in general it isn't easy. You can simplify everything. How can you simplify your life? You can simplify your life starting from alpha 1. You can change it later, or because operation amplifiers are not so expensive, you can add one more stage, pure linear amplifier. If you set alpha 1, alpha minus 1 F3 equals to 0, meaning what you can, in general, you can omit this divider 1 minus alpha F3. You can set your amplifier to ratio 1. It's a lower design in megahertz range. The operation amplifier is reduced to something like a meter, repeater circuit. In such case, your transfer function, if you set amplification ratio 1, your transfer function will be 1 divided by 1 plus omega C1 F1 plus F2 normalized frequency plus omega G square R1, R2, C1, C2 normalized frequency. Because capacitor rho is limited, When you start to change your components, you will find one interesting moment. I hope I can repeat. For resistors, you have how to say it? You have them available in step 1% without any problem. High precision capacitors are expensive. And that's not all. You need to order them on demand, really. Variety, the smallest variety will be for coils. Very small, really. Second one are capacitors, and for with capacitors, you will see this problem. Capacitors are available in much shorter variety compared to resistors. If you need something specific outside of normalized row, you will need to get it on wait for, because it should be manufactured on demand, and it will be very expensive. One more moment, manufacturers of capacitors, they don't like small orders. They have optimum, actually, nowadays, on demand are mostly manufactured microsilver or something demanded by acoustic industry, and they have minimal load of their vacuum, the impregnation chambers. If your order is less than minimal load of impregnation chamber, they may put you on waiting list, on very long waiting list. So start your design from capacitors. Open catalog and select something from standard normalized row. So you will get what? DC mode equation rate 1, L1 should be becomes equal to L2 and you can get it as stop, because we need to solve. It will be A1 C1 plus minus square root A1 square C2 square minus 4 B1 C1 C2 divided by 4P knee frequency C1 C2. One moment, you cannot allow imaginary parts in this resistance. They should be real. That's me. What? Ratio C2 to C1 should be greater or equal to 4B1 divided by A1 square. B and A from your, which form of polynomial you use. This A and B, I should look back, you choose your polynomial. Butterworth, Chebyshev or Bessel. The independence of what polynomial you choose, you will get B and A. Butterworth filters are available as already as ACs. Ready ACs more than you can select from range of frequency. Actually, you can get programmable filter AC with 128 or 256 frequencies from somewhere about up to 25 kilohertz. Selectable frequency. They are available as ready for use integral circuits. If you like make your own custom, you can simplify your life. One of the simplification tricks is to select L1 equals to L2, will be simple L, and C1 equal to C2. In this case, you play with alpha. Changing alpha can, with alpha you can select your polynomial function. What you need? You need faster cut or you need less disturbance. So you select Butterworth or Bessel, simply playing with alpha. Your transfer function will be alpha divided by 1 plus cutoff frequency Fc 3 minus alpha normalized frequency plus omega s Fc square of normalized frequency. So where you will be? Fc equals to square root B1 divided by double P F gun and alpha 3 minus A1 divided by square root of B1. So, alpha here depends only on Q, on quality factor of the internal force. But be aware, this schematic has a, how to say, black point. If you choose alpha 3, it will become a signal generator. It will generate on frequency 1 divided by double P Fc. So avoid values of 3. Avoid values of 3, and one more moment. If you like Chebyshev filter, stick to high precision resistance, because you will be in proximity of this self-oscillation point. What good with this filter? They are easy easily adjustable because you need to change only R1, R2. Some designers incorporate double potentiometer, simple adjustable screwdriver. It's better, it's very good for acoustics, but if you need adjustable filter, you can do it easily with manipulated R1, R2 only. One more moment, this type of filter is easily invertible. If you swap capacitors with resistors, you will get high pass filter with same characteristic. If you need high pass filter, simple perform a swap. Just for knowledge for this type of design, alpha 1.268 corresponds to Besser 2.234 Chebyshev, and Butterworth will be 1.586, but it's for Butterworth. Okay, if needed, what I like to say, if needed, if you need very fast cutoff, if you need this characteristic to go down fast, you, of course, you will think about conversion of filters in series. Their characteristic will be multiplied. Resulting characteristic is not sum but product of filter characteristic. But you cannot simple attach second order to second order. You will need to design fourth order filter. And better find good software. It's a tricky job. I'd like to show one because I'm a bit limited in time. Band pass filter. If you have already some knowledge on low pass filters, every low pass filter can be converted into band pass filter. If you perform a swap, substitute normalized frequency with 1 divided by delta omega normalized p normalized plus 1 divided by p normalized, what will happen? You live with characteristic like this. It's a normalized frequency in logarithmic scale. Yeah? Point here, this is level -3 decibel. It equals to 1 at normalized frequency. Here is the, how to say, basic point for normalization. It's a magnitude of transfer function, this chart. If you perform this substitution, you will get something like this. Here is 0.1 normalized frequency. -3 decibel max. Let's say this is normalized max. This point is normalized mean of normalized frequency. This is normalized then delta omega normalized. So it's set on -3 decibel level. It's kind of mirroring our characteristic. Normalized frequency max divided by normalized frequency mean will be 1/2 square root delta normalized square plus 4 plus minus delta almost by half. Oops. Yes. Okay. So, if you take transfer, it should be normalized function of simple, this is simple LPF filter. If you convert it to bandpass filter, Simple first order LP filter. If you perform this transform to this filter, you will get bandpass filter, but bandpass filter of second order. For this filter, transfer function as a function of normalized complex frequency will be DC transfer 1 plus delta omega normalized band normalized frequency plus 1 divided by normalized complex frequency. It will yield DC transfer delta omega normalized complex frequency 1 plus delta omega normalized frequency plus square of normalized frequency. Basic characteristics are transfer at resonance frequency at the same and quality Q. At a resonance frequency, transfer when frequency is resonant equals to its DC. Transfer, it's easy. And this kind of filter will have zero phase shift at resonance frequency. For us, it may be important. For quality parameter, as an analogue to AC resonant contour, quality may be 1 divided by omega normalized minimum minus omega normalized maximum. So it will be 1 divided by delta omega. So here, transfer function can be written as transfer function value at point of resonance divided by our filter quality normalized frequency divided 1 plus 1 divided by quality normalized frequency plus normalized frequency squared. And this opens for us road to determine all parameters photo. If you need narrow band, you can think, oh, I will combine 2 second order LPFs transfer. This will yield you 4th order bandpass filter. Honestly, better do it numerically. So, if you need band operation, first at analog processing stage, use a 2nd order bandpass filter, perform preliminary cut, and then in numeric part, apply one more filter and cut your frequency. I just will give small example of C. This ratio of 1. Capacitors are equal. R divided by alpha, ground, here output. For this type of filter at alpha 1, you will have quality approximately 1/2. But it's enough, actually it's enough for preliminary. Keep mass processing, better do numerical. For design, 1 second. Its transfer function is alpha frequency Rc divided by 1 plus alpha square divided by alpha PRC plus ERC squared. Here is transfer function. For higher qualities, it is possible to use multiple loop. Example of poly loop. R1, R3 ground, capacitor R2 output. Here, multi-loop negative feedback. Resonance frequency here, 1 divided double P R1 plus R3 R1 R2 R3, and quality of the circuit. Of this circuit will be 1/2 square root R2 L1 plus L3 divided by L1, L3. Frequency band, so delta F, it's at level -3 decibel, will be 1 divided by P L2C. This simple bandpass filter, it will work. Again, if you need seriously, you're looking seriously to perform harmonic selection, something like this, do it better in 2 stages. On modern equipment, it's not a problem. Don't follow old timers where all this bandpass selection were done analog. Old time analog both ACP and processor were slow because at this era 4th order filter was considered as a very high load. It was done in analog part. Now it's not necessary. Okay, I had a bad news. My boss called me. They want me to talk about something serious because that's why I have to cut this lecture short. Next time, actually next time would be better to see one device with well-developed analog processing part, where, how to say, center of weight is shifted towards analog processing, and then ADC and all others. But okay, I have to cut